Hey students, today we're going to do section 4.4 in our textbook, that is solving systems of linear equations in 3 variables. Hopefully you've already done some systems of equations in 2 variables. If not, that's okay. Solving systems of linear equations in 3 variables just takes a lot of record keeping and just really keeping track of what it is you're doing. So if you're a very organized person, this might come a little easier to you than if you are not so organized. You might need to develop a system so that you don't lose track of what you're doing as you work through these problems. So let me share my screen with you, just to give you an idea of what systems of linear equations are. So a linear equation means that each variable is only raised to the power of 1. All right, that's what makes it linear. A linear equation in 3 variables is a graph. Graphically is a plane in 3-dimensional space. So it's like a piece of paper in space. The solution to a system of 3 linear equations in 3 variables is going to be a point in 3-dimensional space. And we define a point in 3-dimensional space using 3 coordinates. So the solution to these systems is going to be an ordered triple, just meaning a value for x, a value for y, and a value for z that makes all 3 of our equations true. All right. So that's what we're doing here. We've got 3 equations, we've got 3 variables, and we want to figure out the values for x, y, and z that will make all 3 of these equations true. All right. Here we have an example of what a system of linear equations in 3 variables looks like. Generally, when we work with these, they're going to be written in standard form, which is your x term, your y term, your z term, and then your constant term is going to be on the other side of the equal sign. Okay. If you are presented with a system where it's not in this organization, you might want to ask yourself why. Maybe they give you a reason for that, or you might need to reorg it so it's x, y, z equals constant term. Okay. Let's take a look at what graphically these solutions look like. So each one of those equations, its graph is a plane in 3-dimensional space. All right. So we have 3 planes in 3-dimensional space, and we want to find one point in space that is on all 3 of those planes. That's essentially what that XYZ coordinate solution is it's that single point in space where all of our equations exist. So their graphs exist. So if we have just a nice one solution situation, it's going to look like this first picture here, where we've got 3 planes in space. They intersect at exactly one point, and we want to figure out what that point is. There are some other things that can happen in 3-dimensional space, though. It's possible that all 3 of our planes intersect along a line. And remember, there's infinite points on a line, so it's possible to have infinite solutions, but that doesn't mean that every value is a solution. It's just that there's infinite solutions as long as all the solutions fall on this line. Okay. There's also a possibility that we have no solutions, right? You can see from these 3 pictures how we could have 3 planes in space that never all 3 overlap in one point. Okay, they could overlap at different points, or if they're all parallel planes, they're never going to overlap. And I'm going to show you some examples of a system of equations where you have infinite solutions, which is what we call dependent, or when you have no solution, which is what we call inconsistent. I'm going to show you what that looks like algebraically, so you'll be able to identify it. Okay. So before we get started on that first example, let's talk about how we're going to tackle this problem, right? So we want to figure out the X, Y, Z variables, the values of X, Y, and Z that make all three of those equations true at the same time. We have two methods that we use, and a lot of times we're going to kind of use both of them at the same time. You can use them interchangeably. One is called elimination, and the other is called substitution. Really, when we are doing either of these methods, our goal is to get rid of variables, create new equations that just have a single variable. Once we have one equation with a single variable, we can solve that equation and actually get a numerical value for that variable. Once we get a numerical value for one variable, then it becomes easier and easier to solve for the other two variables, okay? So elimination is a technique where we add multiples of one of our equations to the other equation in order to eliminate one of our variables, okay? So say we have a x in one equation and a negative x in another equation. If we add those two equations together, the x and the negative x are going to cancel out, and we're going to get a new equation that has eliminated x, okay? Usually when we use elimination, since we have three equations, we're going to pair two of them to eliminate one of our variables. And then we're going to pick another two, just not the same exact two, and eliminate that very same variable. So you can choose to eliminate x, you can choose to eliminate y, or you can choose to eliminate z, but you have to do it twice using two different equations and eliminate the same variable twice. And then you get two new equations that have the same two remaining variables. And one more time, you're going to eliminate another remaining variable until you just have one equation and one variable. So that's how elimination works. Usually once you get to that point using elimination, then you've got the value, the numerical value for one of your variables. Now is a good time to employ substitution. Substitution is where we rearrange an equation or solve an equation for one variable, sometimes in terms of the other variables, sometimes just in terms of a number. And then you plug that in to another equation to further solve that equation, okay? There's a lot of flexibility here, and there's a lot of routes to a solution, okay? So just because I choose one route to a solution doesn't mean that you have to. Really what you want to do when you get started is take a look and kind of plan out your route to try to make it the easiest route possible. What's important though is that you maintain equality about the equal sign. So everything that we do, we have to keep in mind that that equal sign has to continually be true, otherwise everything falls apart. So to maintain equality about the equal sign, that means we can multiply both sides of an equation by some constant term. That's totally fine. Or we can add the same thing to both sides of an equation. And when we add the same thing to both sides of the equation, oftentimes what we're actually adding is another equation. So we have one equation that tells us two sides are equal. So if I add one side to another equation here and one side to another equation here, since both of those sides are equal, I can do that. And then we can always substitute equal values for variables. For example, if we know that x equals 2, we can replace all our x's with the value of 2 because we know that they are equal. Okay, but really you want to keep track of where is your equal sign in your equation and make sure that you are maintaining that equality. Okay. All of this will hopefully start to make sense once we get to our example. So our first example, we're going to have these three equations. I'm going to label the first equation A, and I'm going to try to write that one in red. And then the second equation will be B in blue, and the third equation will be C in green. I like to call them A, B, and C just so I can tell you what I'm doing by saying, I'm going to do this to equation A, or I'm going to do this to equation B, okay? I do suggest for you when you're doing your work getting started to label them A, B, and C, and then keep track of what you are doing by saying, I'm doing this to A, this to B, this to C, okay? So let's get started. All right, so we've got our 3 equations here, and I marked them in, I labeled them A, B, and C. So what we want to do is pick 2 of our equations and eliminate one of the variables. Okay, then we want to pick another 2 equations and eliminate that same variable. And in both instances, we're going to get an equation that now only has 2 remaining variables. Okay. The way I like to do this is to kind of pick both pairs first. So some things that we can think about. I can use this x, and if I multiply this equation by -2, then when I add equation B to equation C, it'll eliminate the x's. Then I could use this x, multiply this equation by -3, add it to equation A, and eliminate the x there. So I could pair B and C, and I could pair A and B, and in both instances, eliminate an x to get my 2 new equations that don't have an x. I could do the same thing with the y in equation A. I could pair equation A and B, and I could pair equation A and C to eliminate the y's. Okay. I could also do that with our z, right? So I kind of like to look ahead to see where I'm going to be able to make 2 pairs of equations that can eliminate the same variable without having to multiply by some weird number. Notice that if I tried to use pair equations C and A to eliminate our x's, I would have to multiply equation C by -3/2 to get a -3x here to cancel out that 3x. So that would be really awkward. So that's why I'm kind of looking at, okay, this x here, I can use that to pair with both equations to eliminate x. This y, I could eliminate these y's. Or really, this z can you use to eliminate the z's in either of the other 2 equations. This red z, I could use to eliminate the z in either of the other 2 equations. Okay, but I'm going to use the z because it's already negative, which is kind of nice. I will start off with, I'm going to add equations A and B in order to eliminate these z's. Okay, and so when I write that, I like to make a new equation, which I call equation A plus B. So this new equation, which is A plus B, when I add A plus B, I'm going to add 3x plus x. So I'm going to get A, 4x. I'm going to add a -y plus a 2y. So I'm going to get just one positive y. And when I add positive z plus negative z, I'm not going to get any z's. Nice, right? And so then I'm just going to say that that equals -15 plus 1, which is going to be -14. Okay. So here I've eliminated x. So now I want to eliminate x again, but I need to use a different 2 equations. I'm still going to use equation B because that negative, or actually, you know what, let's use equation A because we've got a positive z and a negative here, so I won't have to multiply by any negative numbers. So let's use equation A, but we're going to multiply it by 2. So I'm going to go 2 times A, 2 times A, and then I'm going to add that to equation C to get ourselves another new equation. So 2 times A plus C. So 2 times 3x is 6x plus 2x. That's going to give us an okay. 2 times -y plus 3y. So it's going to be -2y plus 3y. That's going to give us just a positive y. Okay. And then 2 times z is 2z plus -2z. That cancels out our z's. We have no z's here. And then we're going to go 2 times -15 is going to be -30 plus 0. It's going to be -30. All right. So we did elimination twice using two different combinations of equations, but we eliminated z, the same variable, both times. Now we're in one step simpler situation. Instead of 3 equations and 3 variables, we've got ourselves down to 2 equations and 2 variables. We're just going to do this elimination step one more time, and then we're going to have 1 equation in 1 variable. So for this elimination step, I am going to eliminate a y. So we've got a positive y here and a positive y here. So I need to multiply one of these equations by a negative number to get a negative y that will cancel out. So I'm going to multiply my second equation by a negative number. So I'm going to say -1 times my equation that is the 2a plus c. I'm going to multiply that equation by -1, and then I'm going to add that to my other equation that is the a plus b. And you know what? Instead of doing it like this, here's another technique. We can rename our new equations. Let's rename our new equations. Let's call this first guy, let's call this guy D, and let's call this guy E. So now what I'm going to do, oops, I think I lost a Y there. So instead of that complicated new naming, now that we've called these new equations D and E, I'm going to add D, or I'm going to do D minus E. That's what this new equation is, D minus E. So we've got a 4x minus an 8x. That's going to give us a -4x. We've got a y minus a y. No more y's left. And we've got a -14 minus -30. So it's going to give us a +16. So this new equation here is our D minus E. And it's 1 equation and 1 variable. Okay. From here, we can solve for the x by dividing by -4, and we get that x equals -4. Okay. So all in all, we had to do elimination 3 times, right? And got those 3 new equations. But by doing that, we are able to solve for a single variable, seeing that x is -4. Once we know that x is -4, now we can plug it back in to any of our other equations to figure out values for y or for z. Since we have equations that are just in terms of x and y, if we plug in our x equals -4 into this guy here, we can solve for y. So let's take this equation over here. It is 4x plus y equals -14. But we know that x is -4, so I'm just going to replace that x with a -4. And now we can solve this equation for y. We've got -16 plus y equals -14. So that tells us that our y is equal to 2. All right. So now we're using substitution. So we've got that x equals -4, and we've got that y equals 2. And we can use both those facts to come back into any of our 3 original equations and plug in a value for x, a value for y, and figure out a value for z. I'm going to use this middle equation just because it looks like the simplest, but I literally could plug in x is -4, y is 2, and solve for z in any of these 3 equations, and I should get the same value. Okay. So let's go with our middle equation, this guy right here, and let's take him to the side. So we've got x plus 2y minus z equals 1. Oops. Equals 1, but we're going to replace our x with a -4, and we're going to replace our y with a 2. Okay, so now we've got -4 plus 4 minus z equals 1. Well, that's 0 minus z equals 1. So if negative z equals 1, then we know z is -1. Z is -1, and we can just box that guy in. And we've got our 3 answers. So x is -4, y is 2, z is -1. And if we want to write that as a coordinate in 3-dimensional space, we'll do our x, our y, and our z. And that is our solution to these 3 equations in 3 variables. It's a good idea once you get here to just go back into one of your other equations or both and make sure that if x is -4, y is 2, and z is -1, that this equation still equals 0. And if x is -4, y is 2, and z is -1, that this equation still equals -15. Okay. So you definitely want to go back and check those, and then you'll know you have the solution, right? So it's not too bad. A little combination of the elimination and the substitution gets you your solutions. Just be strategic when you do this elimination so that we've already planned out that we've got 2 pairs to use to eliminate the same variable. And then also, when I do things like multiply by this 2a plus c, if you can't in your head do 2 times 3x plus 2x, if you can't do that in your head, write 2a, make the equation 2a over on the side. So 2a is basically going to be 6x minus 2y plus 2z equals -30. If you want to write out what 2a is on the side and then add that to c, you can do that as well. Okay. So that is solving equations in 3 variables using substitution and elimination. Let me show you a few more examples of when we have some different stuff going on. All right. So here's the example we just did. Remember how I showed you that there are some situations where we don't have any solutions because the graph of this plane never intersects with the graphs of the other planes. That's what we call inconsistent, and there's going to be no solution. So how can we know that that's going to happen? Well, here I've kind of pointed out how if we do equation -a times c, so if we look at this and we think, okay, let's try to cancel out our x's, right? So I do -1 times equation a and I add that to c. I'm actually going to end up with a 6y plus z equals, what is that, 17? So I would get a new equation that says 6y plus z equals 17, but equation B says 6y plus z equals 12. Both of those things can't be true. So you're going to get some contradictory information. You're going to get statements that contradict each other. If you get contradicting statements, then you have an inconsistent system, which means there is no solution because they will never all overlap. Okay. Then we have what we call a dependent example where there's infinite solutions. And in this example here, if you take a look, you'll notice that all equations are going to be multiples of each other, or really if any 2 of your equations are multiples of each other, you're going to have a dependent situation. So take a look. If I add equation B and C, I'm actually going to get equation A. All right. So because the equations are multiples of each other, something's overlapping. Some of these graphs are overlapping and they're identical planes. So we are not going to have one single example. Here you'd say dependent infinite solutions. Okay. Right. Take your time working through that first example again. If you want to do that example on your own to see if you can get the same answer and kind of analyze, if you're not getting the same answer, Analyze where you're going wrong. Are you making simple math errors when you're multiplying by 2 or multiplying by -2? If you're making simple math errors, then you just need to be more careful. Trust me, it pays to go slow, be careful, and check your work as you go versus getting all the way to the end and realizing something's wrong. Okay, so every step, check your work, make sure that you distributed to every term that you're multiplying by, and that your negative numbers, you're being really careful with your negative numbers. All right. Okay, let me show you just one more little piece of an in-depth walkthrough that I have for you. I'm not sure how well this is going to show up on your screen. But here's another example. I know it looks similar, but it is ever so slightly different, that kind of maps out the strategy, maybe more visually, if you need to visually see kind of what we did in that last slide. This is a different example, different answers. So we have our 3 equations. We're going to use that first step. We're going to use elimination twice to reduce our problem into 2 equations and 2 variables. So I took -3 times equation B plus equation A. And you see that this equation here is -3 times our equation B. All right. And then I add that to equation A to eliminate the x's. And I get this new equation that doesn't have an x. Then I'm going to eliminate x again. And here I'm going to use equations B and C. So I multiply equation B by -2 this time, so that our x's will cancel. And see, I've rewritten what equation B times -2 looks like. And every term had to get multiplied by -2. Then we add that to equation C. So now in black, we've got these 2 new equations that don't have x's. Keep in mind, my original A, B, and C are the same. When I multiplied B by -2, that was just to create this new equation that I'm going to add to C. When I multiplied B by -3, that was just to create this new equation that I'm going to add to A. All right, but my original B is still B. Right. So now I got these 2 new equations. I did elimination twice, got 2 new equations that don't have x. I take those 2 new equations that are just in 2 variables, y and z, and I'm going to use them to cancel out the y's. Notice that I have a positive 5y here and a positive 5y here. So I had to multiply my first equation by a -1. So I changed the sign on every single term, so that when I add these 2 equations together, my y's cancel out. And I just get that 9z equals 9. Solve that, z equals 1. Once you get that first piece, then you just start substituting back into your equations. If we know z equals 1, we could take either one of these that are in terms of z and y, plug in that 1, and we can get that y is 2. Now we know that z is 1, y is 2, and we're going to go back into any of our original 3 equations, plug in that z is 1, y is 2, and we will be able to solve for x. Okay. So if you have your notes, if you can see the notes in Canvas, this walkthrough is in your notes in Canvas. Take some time to look at it to see this technique. This stuff takes practice and you have to be really careful. So I would suggest don't work on this at midnight. Instead, maybe set your alarm an hour earlier than everyone else in your house. Get a nice cup of coffee or tea and sit in a quiet room and try to work through one problem carefully and slowly. Okay. Good luck with everything.